Resilience engineering as a way to deal with safety in complex systems really started around 2000, where NASA had a series of mishaps in 1999. Now, think about where you stand today as an effective organization in relationship to NASA 20 years ago. This is a slide from one of the meetings we held in the aftermath of those mishaps. NASA exists in a changing environment under performance demands and resource pressures, driving down costs, new aggressive schedules, new partners and relationships, new roles, changing skill sets and forms of expertise that are needed, heightened stakeholder interest. Right? Now, what happened there at NASA in those days? Well, in the 1999 space exploration accidents, the independent investigations found we had increasingly brittle systems under faster, better, cheaper pressure. And the organization's inability to come to grips with this new kind of challenge, even though we tried starting in 2000, right? The diagnosis was repeated, and I was an advisor to the Columbia Accident Investigation Board in the tragedy of the Columbia accident. In these cases, right, people were discounting evidence that they were operating outside their competence envelope, right? Their envelope of where they had understood and assessed a variety of threats to safety. Debris strikes for Columbia. We were being more and more successful over time. So what happened? We started to have a different kind of debris strike the orbiter at a different phase of flight with energy levels well outside the boundaries we had investigated and assessed in our engineering analyses. Yet we kept rationalizing these away under faster, better, cheaper production pressure, right? So this is not unique to NASA in 2000. You're under these kinds of pressures. Every organization is under these pressures because resources are finite and change keeps going. And we become more successful over time, which other stakeholders take advantage of to ask us to do more and do it in more complicated ways. Resilience engineering as an approach to safety grew out of those events. So our stance and perspective is, how do we adapt to cope with complexity? We have a lot of success in terms of empirical findings and patterns. This is built on multiple lines of inquiry. I started with cognitive aspects of this and how people and machines work together. But there's biological, control system, networks, right, and larger scale human system findings that all contribute to this. And at the heart of those findings is we need to think of these systems as layered networks. And as we'll see in a moment, they're kind of tangled and rather messy. Now there's a science base that's developing, and this was happening even around 2000 as well, partly from the empirical results, but a lot of these are fundamental laws, fundamental hard constraints about the way this world works when we look at it from the point of view of an adaptive system in a complex world. Now, what that leads us to and what we've been trying to build is a kind of humble but different integrated systems engineering. Humble in the sense of doing all the traditional basic thorough steps when we engineer systems that carry out risky, difficult services. But it has to be different because the linear assumptions we used to make in our engineering processes don't hold. They don't hold for complex worlds. So we have to have some different ways to approach our integrated system challenges. And that leads us to pragmatic engineering capabilities that we use to outmaneuver the complexity penalties that we just illustrated in NASA's history. Now, we want to debate the word resilience. And when we started using it in 2000, we knew it would be popular, but we had no idea how hyper popular it would get. So before we get into some issues about resilience, the actual definition that matters is adaptive capacity. How systems need to be poised to adapt, that surprise is inevitable, that however we understand our system and our models of it and what our understanding of safety is and threats to safety and how well we have those under control, surprise, challenge, anomalies will occur. So adaptive capacity is related to not how we can change our models, plans, processes, behaviors, right, beyond the way the system currently works in order to fit the fact that situations will change, anomalies and surprises will occur, newer relationships will arise. This potential for adaptive action in the future is at the heart of a resilience stance and approach to understanding modern complex systems and making them work safely. Now, a lot of our data comes from studying places like cockpits and air traffic control centers and mission control for space operations and military command centers and wildland firefighting, et cetera. We have a real basis for this. And what are some of the findings? And I can barely touch on a couple of these. But one is, right, when we look at these systems, there are extensive and hidden interdependencies, and the extensiveness of these interdependencies and how many of them are hidden keep increasing as our capabilities increase. As a modern software service architectures person said recently, every time I work on my continuous integration development software projects, I'm blown away by the unseen dependency spaghetti messes hidden in my software infrastructure. And this is just one world where this plays out. It plays out at the level of human social interactions, in new cyber threats, in a variety of kinds of things that are going on all around us. A very simple way to think about this, and again, we're putting it in the context of software intensive systems, is no plan survives first contact with a disaster in the making. Back to those NASA cases. Perfect software, when it makes contact with real production traffic, turns into, sometimes it falls apart. And this has happened, for example, in the airline industry. And we've had multiple airlines go down due to IT failures costing them hundreds upon hundreds of millions of dollars. And there's no way you can come back and say this was a person or this was a single event. Those are misreadings of how these kinds of problems arise. Instead, these are emergent phenomena that arise from the characteristics of these as a network, how they're brittle, how we try to make them more robust. We have sources of resilience, and we sometimes undermine those sources of resilience. Now, that one example is, I could fill up screen after screen with examples in financial systems, highly automated, highly autonomous, right? Hospitals, cloud computing. This happens to Facebook and Amazon and everyone who has outages and surprise, just like we have accidents occasionally and unfortunately and tragically in aviation. What's this reminding us of is, rather than our usual assumption when we take linear approaches, is that systems are messy and some people provide the source of resilient performance. Right? This sign captures it for us. The system was never broken, it was built this way. Well, the military had a phrase for this from World War II. You remember it all. Snafu, situation normal, all left up. Snafu is the normal state of systems, due to the fact there's always finite resources, there's always change, there's always new pressures from stakeholders to do more, do it faster, do it in more complicated ways in order to provide better productivity, efficiency, and other sources of value. So systems have to be poised to adapt. If snafu is normal, we then have a challenge, a question. Wait a minute. Why don't we have more failures? I mean, yeah, I just gave you a list of a bunch of the kinds of breakdowns that occur in software-intensive modern distributed systems. Why don't we have even more? Well, the answer is systems operate successfully due to the extra adaptive capacity that people bring that's usually hidden or underappreciated. That's called the fluency law, right? Well-adapted activity occurs with a facility that hides the difficulty of the demands resolved and the dilemmas balanced. A law about how adaptive systems work. So our ability to adapt, to handle the messiness as systems grow, change, get more efficient, get more interconnected, right, becomes invisible to other stakeholders and roles. So we tend to miss snafu catching. So snafu is a normal state of systems. Snafu catching is an essential activity. And where do we get it? Most of the time in most systems, we get it from some people. Let's step back now and take a look at different ways people talk about the word resilience. So there's 4 different ways people have used the word resilience, basically. One is the common one of rebound from a shock event or trauma event, the aftermath of an extreme weather event. How do we recover? And we want to bounce back quickly and more thoroughly. But this is a societal need. It doesn't express anything about where does that ability to come from to recover and adjust. A second way we think about it is robustness. And we often find people confounding robustness with resilience. And that becomes very important in the new kind of humble but different systems engineering we need to do. Keeping robustness and resilience separate, very important. Robustness adjusts the competence envelope to handle new sources of disruptions that we understand. So we analyze and look at these in detail. In the Columbia accident, it would be understanding the new debris strikes on launch from the booster rocket insulation, in order to understand its potential for damaging the orbiter. Instead of carrying out those additional analyses to adjust the competence envelope to handle a new source of disruption, a new threat, instead it was rationalized away. And that's laid out very nicely in the Columbia accident report. Now, the advanced and more technically grounded in terms of the science are two different ways to think about the word resilience. And these are focused on adaptive systems being poised to adapt, and they're starting with the nonlinear nature of this universe. The first one is graceful extensibility. And that means, again, finite resources means however successful you've been, there are still boundaries and limits on how that system works. So you need a capability to stretch or extend near the edges. Right? Where are those edges? And you will be surprised by anomalies, exceptions, and other kinds of challenge events, including opportunities. And so how do you extend performance and gracefully do that as situations arise and challenge? These are the kinds of the small challenges are arising all the time. And snafu catching, right, is that kind of graceful extensibility that's going on at the edges. So we stretch at the edges when the system's under stress. Very simple. Stretch at the edges when the system's under stress. That's what that sense of resilience is all about. Right. And since then, some of the theorists and the underlying science have highlighted we have an architecture issue of what kind of system can continue to adapt over longer term cycles of change, right, given the kinds of hard trade-offs that we face. So let's illustrate this with a simple animation. Right. However we set up the system, we can think of it as a plan. However it's embodied in procedures, automation, latest AI, whatever. And when we look through the plan at our world, whatever operational world it is, it's always springtime, the leaves are always out, the flowers are always blooming, it looks great, right? But there's an edge to that. And what's just beyond the edge, right, is some people doing the dragon taming, the snafu catching, that our system is at risk of a variety of things. And often those fall outside what we've planned for. If we turn around and take the view of the people wrestling with dragons, right, doing snafu catching, they're often looking back at the people admiring the beauty of their plan and how much better it has been than in the past, right, as we continue to develop and get more reliable and more efficient. And they're constantly going, hey, I could use a little help over here, right? So these two positions capture what's critical about adaptive systems and adaptive capacity, right? We need to build better plans and embody them in more thorough, more effective ways. But we also have to recognize there's limits to those plans, and the world will throw curveballs at us. As Yogi Berra put it, even if the world were perfect, it wouldn't be. And so we need to support snafu catching. Oftentimes we miss it and we inadvertently undermine it, or we take it for granted. So now at this stage, everybody should be going, well, I can understand that. And yeah, that comes up sometimes, but maybe that doesn't really apply to us, right? Why? Well, we find that organizations tend to use three grounds to rationalize this away: rarity, prevention, and compliance. Right? Well, snafus only occur rarely given our design. Thus, we don't need to invest very much in this. Or we have a record of improvement. And that continuous improvement means we don't have much likelihood of difficult or severe snafus to deal with. Or when they occur, yes, they occur, but the poor response is really due to people, right? They didn't work to the rules for their role. And if they just work to rule and work to role, everything would be fine. Well, these are wrong in the complex world and the way we've understood it in the science base. They're wrong empirically. We keep observing this technically, as well as the formal theories and theorems behind this. So where do we end up with? Back to our last point, pragmatics. There are ways to outmaneuver complexity. And these are very relevant to your context. One is the spaghetti limit, right? But there's ways to cope with that. Techniques are being discovered are being developed to uncover the hidden interdependencies through new forms of testing. Guess one of the places where this is becoming prevalent and used widely, it's in the software intensive systems. And this is one of the places where resilience engineering has had the biggest and most profound pragmatic impact. Why reliable systems fail. We have to unconfound reliability, robustness, and resilience as this graceful extensibility. So we've done that in a world related to you with introducing drones into controlled airspace by developing a new kind of trade space study, something typical in systems engineering, but we have to change it for a complex world. So we now developed ways to do resiliency trade space studies and incorporate the new requirements for adaptive capacity into our designs of our system as a network of multiple roles and machines carrying out a wide range of activities safely and with greater efficiency and capability. Safety management, right? There's a new piece out on how to build safety management in this continuous and guided adaptability role. And this is practical guidance for everyday safety managers who work in many different kinds of organizations. It's being used extensively in a variety of industries in Australia, for example. And then we have new kinds of shared control architectures where we actually build new control systems. And so we published a recent example of this that solves a classic problem in automatic flight control and automation pilot interaction that has caused incidents and accidents previously. Equations. We can even give you equations on some of these things. So let's go over what we've covered, all right? When you use the word resilience, remember, which family are you referring to? They all bring some positive aspect to our pursuit of more robust, reliable systems that carry out risky and productive activities. Are you doing rebound from disrupting traumatic events? Are you able to manage more of the stressors that are well modeled to make a system more robust in its competence, basic competence? Or are you bringing extra adaptive capacity to bear when surprise events challenge the boundary conditions? Can you adapt to future surprises as conditions continue to change and evolve? Being poised to adapt, right? It's a critical priority for all organizations in today's increasingly complex and interconnected world, building and sustaining your system's adaptive capacities. So what have we covered? Empirical patterns on adapting to cope with complexity. Snafu catching is essential. There are fundamental laws and hard constraints. We barely scratch the surface. Humble but different integrated systems engineering. Real capabilities are being developed as we speak to outmaneuver complexity penalties. Thank you.